Hi, everyone. My name is Cecilia Dome, and welcome to the National Science Foundation CityS Lab Research Coordination Network Lunchtime Webinar Series. So I'm very happy to introduce Dr. Callie Babbitt from Rochester Institute of Technology to give our initial, very first webinar talk. The topic is on food waste, creating a sustainable food waste management ecosystem. This is a topic we have our RCN network have found like food has been really not been well considered in the food, energy, water nexus. And with this pandemic, we have seen a lot of issues with food security. And so we decided to focus on this topic. And it's going to be a series on food topics for this fall. And the format is we are going to open this more to the public, and we encourage more students to participate and to look at different perspectives on the food system, especially in urban development, and some innovations and people have been looking into, and how we can do things collaboratively to make this system a more sustainable, and then we can live a better and healthier life. So Callie is an associate professor in the Golisano Institute of Sustainability at Rochester Institute of Technology. She conducts research to proactively quantify and minimize environmental impacts of emerging technologies. Her research group used methods from circular economy, eco-design, and life cycle assessment to study sustainability challenges and create solutions for consumer electronics, plastic wastes, lithium-ion batteries, electrical vehicles, nanomaterials, and food waste management. She has a BS in chemical engineering from Georgia Tech and MS and PhD environmental engineering from University of Florida. Callie is a Fulbright scholar and the recipient of National Science Foundation Career Award and AT&T Technology and Environment Award. So without further ado, I give the baton to Callie to start the talk. Welcome.
Thank you so much for having me. It's really wonderful to connect, especially with such a broad group of people when it's so challenging to connect right now. I'm really happy to be able to share some of our research, and as I'm talking, hopefully the idea behind a food waste ecosystem becomes more clear over the course of the presentation. I want to start by just first giving a quick overview of our Sustainability Institute at RIT, because I'm guessing this may not be something that everyone is familiar with. And so we are a graduate degree granting institute in Rochester, New York. It's within the university, but functions as its own college and institute organized around sustainability. And so our primary focus is graduate training, PhD, master's in both sustainability and sustainable architecture degrees. And the goal of our program is to carry out research and form partnerships that will lead to solving global sustainability challenges. Everything from clean manufacturing to green buildings, like our facility that you see here, to new technologies and solutions for turning waste into resources. So the real goal is using what we would call a systems approach that comprehends sustainability issues at multiple levels, including economics, environment, society, policy, consumers, and education, leveraging all of those different perspectives to solve some of these challenges. Now, when I say a systems perspective, what we're thinking about here, and what I think a lot about, is a life cycle perspective. So not just looking at any given product or system wherever that we might be using it, but rather considering it over its entire life, all the way from raw material extraction, manufacturing. I'm going to just quickly, I'm getting all the notifications of people joining, so I'm just going to quickly hide that. All of manufacturing, transport, distributing, way that consumers use products and resources in their home, and then end of life management through recycling, reuse, or landfill. And ideally, creating a circular economy that closes the loop on resource use across this life cycle, as well as trying to model all of the material, energy, emissions, water that are consumed and are released across the entire life cycle. And so when we think about systems, to apply this systems thinking to food makes a compelling choice. One is because this is a system that's fundamentally inefficient. So if we look across the entire food supply chain, only about 60% of food waste food actually gets consumed, but over 40% of that gets lost. And those losses happen from across the supply chain, all the way from farming to consumption, or farm to fork, as we like to think about it. And so this is a compelling case for creating a closed loop system that will transform the linear system. So when we're thinking about food waste, it's one thing to think about it in percentages, but it's another to really think about the magnitude of this. So every year in the United States, we waste about 66 million metric tons of food. So to give you a better sense of what that looks like, imagine this football stadium, this Rose Bowl stadium, filled to the top with food waste every single day over the course of a year. And so not only is this an immense waste challenge, but its management creates several related sustainability issues. So when this food is managed, it typically goes into a landfill, where in that landfill environment, which is an anaerobic environment, meaning it's free of oxygen, it decays and produces greenhouse gases, including carbon dioxide and methane, which is a global warming gas that has a global warming potential about 25 to 30 times that of CO2. So this is a major driver of climate impacts, and is a key area that we can look at for trying to enact climate solutions. But it's not just about the emissions from the landfill, it's also about what this waste represents. So when we think about food waste, that represents food that could have been used to feed people. It represents immense investment in water, energy, chemicals, fertilizer associated with growing those food, and it represents a huge economic loss. And so again, this really compels us to think about this through a multidisciplinary sustainability lens, because solving the food waste challenge can in itself solve a lot of other related food, energy, water challenges that have social, economic, and environmental dimensions. So as we're starting as RIT and our group is working on solutions for this, we're trying to take three main approaches. First, really figuring out what is lost or wasted along the food supply chain so that we can target solutions to the point of the most waste. Second, identify and implement ways to prevent the losses. In other words, try to stop the food from being wasted before it even happens. And third, trying to find solutions that can valorize inevitable waste, or in other words, create value out of what might have been a waste, turn it into a valuable resource like energy or bioproducts. And this really follows the conventional wisdom of the EPA material management hierarchy that says, the highest priority activities are at the top of this pyramid, and you want to have the most material diverted or managed by the solutions at the top, and less actually ending up requiring landfill at the end of the day. So this was really the motivation for the research that we've been doing at RIT. However, as we began our work in this area, we became concerned that oftentimes solutions are narrowly focused. So if you think about food waste, this is what might come to mind. A recent meal, leftovers, or something, and maybe not so much at a restaurant anymore, but maybe leftovers from cooking or a meal, the spoiled spinach in the bottom of our fridge. But those really only are the tip of the iceberg. And solutions that only focus on one specific piece of this complex challenge are unlikely to have large benefit at a broader scale. And so what we thought about is, how can we actually encompass the entire complexity of this system? So this diagram begins to capture that, and it's even more complex when you start to build in other dimensions. But we can first think about where the waste is coming from across the entire supply chain. We also have to think about the transportation and infrastructure associated with managing it. We have to think about policy. Many states, including New York, have recently enacted food waste policy, mostly targeted at commercial waste generators and not consumers, but that's also happens in many areas. And at the same time, there's other related policies that are also emerging, like climate and energy targets or water quality targets. Then we have a whole spectrum of different technologies at our disposal to use to manage waste in different ways. And each of those technologies has a different potential to be deployed given available infrastructure and logistics, and is going to end up having different environmental, social, and economic outputs. And so simple end of the pipe solutions don't work well when you have a system as complex as this. And so when we were forming this project that I'll be speaking about today, we took a lot of our inspiration from the field of industrial ecology. This is an academic and research domain that uses natural systems as models for industrial systems. If you think about it, nature has already solved many of the problems we face today, from efficient nutrient cycling, conversion of solar energy, and water and resource management. And so if we can take inspiration from those systems, we can think about designing our industrial products and systems in a way that's more regenerative and resilient. And so if we use nature as our inspiration, then we begin to think about responses or models that effectively capture complex systems and can help us model the full cycle of energy, resources, and waste. And so we said, how would an ecologist approach this complex system management? And so if we think about a natural ecosystem, and this is like a super simplistic example here, if we think about this natural ecosystem, you have different species. You have some carnivores and some herbivores, and so resources flow when one organism consumes another and by the products and the materials that they use in the environment. Now, you have a certain structure of those organisms. For example, you have a given biodiversity or a count of different species that's heavily influenced by external pressures like resource limitations or evolution. And then that entire structure really governs how much material and energy flows through the system and how much biomass, which nature doesn't always have waste in the same way that we think about it, but it does create biomass, how much biomass is produced. So if we wanted to then adapt this idea to the food waste ecosystem, it means we have to understand what are all of these industrial species, not just the leftovers at the consumer level, but considering the full supply chain all the way from farm to fork and all the interacting species. For example, if we manage food waste by anaerobic digestion, which I'll talk a little bit more about later, we might make biogas or bioelectricity. So then we have to start comprehending the electricity grid, electricity markets, and climate and energy policy. We have to think about transportation. We have to think about the ultimate releases back into the ecosystem that then feed back into those food production. This entire system, its structure, is really governed by external forces like policy, economics, consumers, and major disruption events like we've seen now with COVID-19. The resulting structure influences the amount of resources that flow through and the ultimate amount of organic or food waste that comes out at the end of pipe. And so this picture really represents the motivation behind the NSF Infuse project that we've been working on for the last several years. And the rest of the talk, I'm going to highlight some of the things that we've found and hope to continue researching and hopefully collaborating with some of you in terms of answering the question of how do we create an ecosystem that will actually recover food waste as a valuable organic resource, minimize some of the sustainability impacts, and create net economic and social benefit for the community. So the first thing in really defining that ecosystem is drawing a geographic boundary or defining the geographic scope. Our project primarily looks at New York State. There are obviously very different challenges from one end of New York to the other, and I'll talk a lot about Western New York, where Rochester is located as well. So we know that the type and the amount of food that's wasted is being generated by these different industrial species in different places. This is a resource called the Organic Resource Locator. It's put out by the New York State Pollution Prevention Institute, and it actually maps the location of all organic waste across the state. So you can see that there's a lot in red dots, which are the confined animal feedlots, where you have cows being raised for dairy or meat, and you have manure that has to be managed. There's also a lot of food processor, restaurants, and other generators across the state. So this really forms the geographic scope. And one of the things that we discovered is, just like in a natural ecosystem, these actors have seasonal variability. And so when we look across New York State, one of the particular challenges is that waste generation changes seasonally. This graph shows supermarkets, K-12 schools, and universities. And as we might expect, these have strong seasonal variation. Schools have a lot more waste being generated during the academic year and a lot less during the summer. Supermarkets have seasonal fluxes that go along with holidays, produce seasons, and things like that. And this is generated by both database coming out of the Organic Resource Locator, as well as empirical data provided by some specific companies in these categories. And this is a particular challenge because this means you can't just have a one-size-fits-all solution. You actually have to have a solution that's adaptive and can be resilient to these seasonal fluctuations. We also found that the waste generation is not consistent across different actors. So again, if you look at all the commercial and institutional generators in New York State, 4% of them contribute 57% of the waste. And so the graph here shows different levels of generation thresholds. So companies that generate between 0 to 24 tons a year, 24 to 47, et cetera. These generation thresholds relate to the New York State food waste policy. And so, which is basically targeting just those that generate the most, or that top bar. And that actually makes sense, because with just a small percent of the facilities in New York, you can capture over half of the waste. To get the remaining percentage, you'd have to do lots more companies. And so you may not get as much bang for your buck. So this gives us some idea about where to prioritize, who are the real keystone species to prioritize. And this also varies depending on the type of generator. So here we see now the same data, but now reorganized according to where the food waste is being produced. Supermarkets are a major piece of this. They're both high in number and in terms of the contribution by mass. So that tells us that supermarkets are a real priority for both finding ways to reduce waste, which might be through mechanisms like changing date labeling on food, better practices for matching supply and demand and inventory, but also they're appropriate to target for policy that would require them to divert food from landfill rather than disposing it. Now, when we then think about the way to design a system that can respond to these variability, that we also have to think different technical constraints as well. So a lot of our research uses geospatial modeling tools to come up with recommendations on how to sort of create a systems level solution. So the graph that is showing now has two main components. The first, which are in the small, kind of dark or lighter green, the small little cells that are heterogeneously distributed across this area. And this is Western New York, Buffalo and Rochester, sort of the centers here. Those small greenish blue areas represent land that would be suitable for building a food waste treatment facility on, whether that's a composting site or a anaerobic digester. So you can't just put these everywhere. They have to be appropriate land conditions. It has to be in certain kinds of development. And then you also want to locate the facility close to where the food is being generated. And so what's really interesting here is there's a real interesting spatial trend where close to where the food is generating, say in these large concentrations of orange and red, Buffalo and Rochester there, there's not a lot of sites that can be used to build facilities. So when you're thinking about this from an urban standpoint, kind of tells you that traditional waste treatment infrastructure doesn't work well in an urban context. It also means you have to start thinking a lot about transportation, because the sites that are ideal for building out infrastructure are distant from those areas. Now, the sort of oval shapes represented about a 25-mile radius from the cities. And that 25-mile radius is, again, related to New York state policy. So beginning next year, companies that generate above this 94 ton a year limit must divert their food waste if they're within 25 miles of a generator or a treatment facility that can take it. If they're not within 25 miles, they can request to be exempted, which also gives us information about where the state should prioritize building out new infrastructure. Now, we also have to think about what technologies to put in those different places. One of the most common technologies in New York is, of course, composting, but at a very large scale, we see a lot of anaerobic digestion. And the reason we see a lot of this in New York is because of all of those feedlots where we have cows being raised. That manure has to be managed, and anaerobic digestion as a technology works very well when you mix together food waste and manure. So I love showing students graphs like this to show how glamorous sustainability research is. And in these facilities, similar processes happen as might happen in a landfill, where you have an absence of oxygen and a microbial degradation to produce natural gas or biogas or methane. And the methane that's produced from this process is very similar chemically to the natural gas that we burn to produce electricity or use for heating and fuels. So if we can actually recover that energy in the form of electricity and sell it back to the grid, or compress and clean it and put it into the pipeline, we're able to then at the same time manage food waste and create a clean energy supply that displaces fossil fuels. So this is a technology that shows a lot of promise, and there's already several commercial scale facilities in New York and other places across the Northeast. One of the challenges, though, however, is when we look at this from a systems level, we start to understand that deploying this at a wide scale is going to lead to serious ecological impact. So currently, when this process runs, the two main products that come out, other than this natural gas that we recover for energy, the other two products are solid and liquid fractions of the digestate. So this is the residual material that's left after the digestion process happens. Right now, in a lot of places, this solid digestate is treated and then used for bedding back where the cows are being housed. And that liquid digestate is very concentrated in nitrogen and phosphorus and other nutrients. So they say, let's put this out on non-edible crops, like crops, fields that are being used to grow corn and soybean to feed animals. And so we can use this in place of fertilizer. Now in New York, however, there's a relatively short growing cycle, and overloading these fields with excessive application during the year can lead to significant water contamination. And so part of our project has been to include the ecological piece as well. So the graphs here show several fields in Western New York where we have done both baseline measurements of the nitrous oxide, nitrogen emissions coming naturally from the land before and after this digestate is applied. And the before is shown here in blue, the after is shown in orange. And you can see that putting this on the fields leads to significant emissions. And these emissions last for a good bit of time. So the right side of this graph then shows the concentrations over a 2-week period. So it takes about 2 weeks for the emissions to return to the levels they were at before the digestate was spread. And so what this tells us is that, if we look to anaerobic digestion as a technology solution, we have to then come up with a better way of handling the liquid effluent that's left at the end of the process. And so one of our students is actually then looking at new technology innovations that could reduce the cost of operation and the impacts, because it's also very expensive for companies to haul this digestate around and apply it. And here what we're looking at is then taking these two separate fractions and converting the solid digestate using a thermochemical process called pyrolysis, which is kind of like burning, but in the absence of oxygen. So you're able to kind of get a char that comes out rather than combustion products. And by making a biochar out of this, we can then tune the properties of that to use to absorb the nutrients that are in that liquid digestate. So we're doing two things here. We're taking the nutrients that were in this liquid and we're absorbing them onto a solid fraction. So these solids are a lot cheaper and easier to transport and use than the liquids are. And then we're actually able to control the application back into the ground as fertilizer. So you're still getting the nutrient recovery potential, but in a much more controlled way. And the research that's ongoing is now looking at whether or not these biochars will actually be able to absorb those nutrients. And then once put back into soil, produce a great desorb and then be accessible for the plants. And our early tests show that you can use this method and enhance the production of certain types of crops. Now, all of these things are very promising, but there are still a number of economic and policy challenges. And so one thing that we're thinking about is this ecosystem has to include policy. And this graph is from a paper done by two of my colleagues on the policy side that are looking at different ways that policy can be used to invest in the deployment of technologies like anaerobic digestion, specifically to produce electricity. There's a lot of interaction here. So if New York has a food waste policy and they have a clean energy target and a climate target, you can start thinking about those things and their interactions. So can we use food waste management to actually make it cheaper or easier to meet certain climate or energy targets? And what they found is that through relatively modest investments like cents per kilowatt, you could actually significantly increase the amount of electricity that could be produced from biogas operation at these anaerobic digesters. And this could be through the way of subsidized loans to build out that, capital cost grants, which the state is already doing a little bit of, where they actually share the capital costs of putting new infrastructure, or even incentives on the electricity generation itself, which was not as effective as some of the others. So policy clearly plays a key role here. The other piece of this is people. And like I said before, sustainability is not always glamorous. And so at the end of the day, people are part of the solution when it comes to separating the food waste out. That might be the workforce, the frontline workforce in those restaurants and grocery stores that are actually separating the food waste. And it's also you and me in our households. So I'm not sure if any of you all are household composters. I'm a diehard composter and my husband's not a super big fan. He thinks it's gross. And it turns out that when we survey consumers, that's a view that's shared by many. So this graph is part of a New York State survey that will eventually go into a theory of planned behavior model around intent to compost. The bottom half of the survey looks at people's attitudes towards composting, and people have a universally positive attitude about it. It will create a better environment for the future. It's a good thing to do. It'll be rewarding. It will reduce landfill. But if you look at the top part, and these are somewhat reversed, people don't really think that it's a very enjoyable thing to do, and they think it's gross. And yuck factor, as we like to call it, it's not been studied that much in the literature. So that's one thing we're looking at. And when we talk to people, even those that separate, say they don't like doing it because they think it might attract rodents. And many non-separators tell us that the yuck factor is even a bigger role than pricing itself when it comes to their decision about composting. And so this means that we have to think about our food waste solutions in the context of people. And so one of our studies is now looking at the growth of organics recycling, especially small businesses that are offering this at the household scale. And scale becomes really interesting here. When we typically think about trash collection, we think about these large trucks and large infrastructure, but organics recycling is happening at lots of scales, even including bicycle pickup, as happens in some places in New York. And so part of our question is then trying to ask, what sort of business models are out there and do they meet consumer needs? There's all kinds of models that we've seen, ranging from different sizes of containers, different models where this kind of gets around the yuck factor that consumers are worried about. The company brings them a clean bucket and they give their old bucket. In some cases, they just swap the liner, in some cases, neither, which creates different barriers to entry. There's a wide range of prices and different models that exist. So part of our research has just started is to really understand what are all the business models out there and do they meet consumer needs? And what's also very interesting about this is that many of these new business models are happening at a very small scale. So the typical engineering logic is that you want to make a really big scale system so that you can take advantage of economies of scale in operating costs and other economic aspects of your system. But in food waste, there's a huge variety of scale. So we have here a picture of a traditional large-scale anaerobic digester and a small-scale pulper that's being deployed at a university cafeteria. So this is taking grinding up the food waste and removing the water, and you're left with a really small piece. So how do these two centralized and decentralized large and small scale systems work together? And can small scale solutions play a role? Another example that sort of speaks to the food system more broadly is our production models. So this is a farm in a box or a freight farm that it uses old shipping containers to grow food. And so part of our question is can this actually reduce life cycle impacts of growing compared to conventional agriculture? And will people like it? Or is this too much of a hassle and too low of a yield to really make a difference? So right now we're carrying out both qualitative research and interviews with adopters, as well as life cycle assessment of the different performance aspects of these systems. And we're also looking at economic tipping points. So again, what's shown here is a food waste dehydrator. This is a really interesting technology that is being explored, especially at the urban scale, where you don't have large docks and facilities to have a lot of big food waste collection. You can actually use these to dehydrate, remove the water from food waste, and what you're left with is a really small, like about 5 to 10% of the initial mass and volume is what comes out. And that amount can be stored without odor until picked up at a later point. The problem is they take a lot of energy to run and they have a high capital cost. So when we compare it to traditional offsite hauling and anaerobic digestion, this only makes economic sense when you get above a certain tipping fee or the amount that a company has to pay for a facility to take their waste. And so what this is all kind of going into this idea of, for this ecosystem to work, there have to be some large actors, there have to be some small actors, and they have to work together in a coordinated way. And finding those, so to speak, niches will be a critical piece to sort of making this system work as a whole. And then I also want to kind of mention some future work. We've just started a project through the NSF Growing Convergent Research Program with 4 other universities to look at circular economy for plastics. And in the food system, the plastic system has a huge interaction. Upstream, packaging plays a key role in preventing food spoilage and preventing waste upstream. So we need smart packaging upstream, but that residual packaging becomes a big problem downstream. And in this picture on the left, you see some like pre-cut vegetables, and then you see some garlic. And in the garlic picture, these are like individually wrapped cloves of garlic. So when we talk to grocery stores like Wegmans, what they tell us is that when their employees see waste in, say, these like large prepackaged things, they're instructed to tear them apart and put that into the digester. But it's not worth their time or effort to take apart each individual piece of garlic and separate it. So that whole bag will end up in the landfill bin. So we have to think about the right way to deploy packaging. On the other side, downstream, you see a picture here of a depackaging equipment. These are costly and have some challenges to run, but they can help businesses save money by allowing them to take in more food waste streams and then recover some of the recyclables to sell. So figuring out the right way to deploy packaging will be a key part of this. And the final thing that I want to mention as I begin to wrap up is that, so far we've kind of talked about these solutions at a practical level, but making all this happen really depends also on education and awareness. So thinking about all the different stakeholders across a system and understanding how they can play a role in it. So a big part of our project is actually trying to work with and translate research back to industrial stakeholders. For those others of you in New York, hope you all are as big of a Wegmans fan as I am, and they're a key partner in doing some of this research. They're very progressive on the food waste side. We also want to broaden public participation and understanding. So one of the really cool projects that we've been working with here at RIT is a project called Sustainable Signs. So RIT is actually home for the National Technical Institute for the Deaf, and we have a huge population of deaf and hard of hearing students and faculty, as well as community members. Turns out there's no sign for food waste or sustainability. So if we want to explain these concepts in a classroom setting, we need to think about how to translate, how to interpret them in the right way. So we've actually developed, working with deaf education, signing, and interpreting experts, a suite of sign language terms that will help explain food waste and sustainability concepts to this audience. We also do a lot of work with schools and helping different schools in the area to deploy and test composting and separation mechanisms in the classroom and cafeteria. And then the other part of this, of course, is curriculum. Being a part of the Sustainability Institute, we're very interested in novel education models to explain these things. So we also have a little bit of flexibility in the classes. And so two of the electives that I've offered, one is about sustainable food, energy, water systems. And we've really looked at our regional system as a case study. Here we are touring FoodLink, which is a major regional food hub. We also had a course recently called Sustainable Spirits. We don't often think about the beverage industry, thinking about alcoholic spirits and not ghosts. We don't often think about the beverage industry, but beer, wine, cider, and spirits also have huge water and waste footprints. And so we're looking at this as a major economic force in the Rochester region, and also a challenge to think about how to manage these materials. Anecdotally, for example, when we talk to breweries, a lot of times their spent grain is sent to farms where it's fed to cows or pigs, depending on dietary needs. However, that's only a system that can accommodate so much resource, and you have to also think about other areas, especially in urban contexts where hauling this low value material out of the city can be very costly. So there's a lot of cool new possibilities that have come out from the education piece as well. And so I just want to, hopefully this has given you kind of a sense of the different research that we're doing in this area. I want to particularly acknowledge our project team. It's very interdisciplinary. This is the core team at RIT, and we do have some collaborators at other universities and these industrial partners, as well as students and the funding from primarily NSF and the New York State Pollution Prevention Institute. I've also provided my contact information here. I'd love to talk more, answer questions, or maybe even explore some collaborations if some of you all are working in similar areas. So I'll stop there. I think there was some interest in having some time for question and answer, I think, Cecilia. So I wanted to stop there and try to open it up for discussion.
Thank you, Callie, for the wonderful talk. I think Nadia is going to collect questions. I think we have a lot of attendees just so that we can sort through all the questions. Nadia, have you received any questions so far you wanted to
Sure.
share with the, go ahead.
Absolutely. Thank you, Callie. It was a great presentation. We appreciate it. So I have received a couple of questions, and if anybody else wants to ask questions, please send me your question and I can read those for Callie. So the first question is from Micah Bobker. He would like to know that your data appears to categorize commercial / institutional sources. So how does the residential or household waste stream fit into your data?
So that's a great question, because we are very fortunate to have access to pretty good data about the commercial sector. It really started with that organic resource locator that I mentioned, which is specific to New York State. And now the EPA has also come out with a great tool that's what they call the excess food opportunities map. So one thing you'll notice is a lot of like clever branding around food waste. We don't want to call it food waste because it has value, but rather organic resource or excess food. So that's kind of intentional, I think, by those stakeholders. But in both of those cases, it's just commercial or institutional. And a lot of that has to do with the methods that they use to calculate that data. Much of that data is based on sort of like limited empirical studies where we go in and actually audit. And the Pollution Prevention Institute has done a lot of this. We go into, say, a hospital or a school. We go to the different, in the back of the house and post-consumer piece, and we actually weigh and measure different kinds of food waste. And that gives us some general estimates. And those estimates are then used to come up with generation factors. So you would say for like a K-12 school, the generation factor is usually some tons of food waste per student multiplied by the number of students that are there. And of course, we don't have those for all sectors, so they kind of come up with averages, and that's what goes into those databases. So our data was a blend of both empirical numbers and these estimates. Unfortunately, however, the household side, the waste estimates there are not as good. And there's been some studies that have looked at sort of reasons for that. A big problem is that there's not a really consistent method for doing that. So the main methods that people use are like a plate count, where they actually like either take images or document what's on their plate, or food diaries, where they actually write, like other like transportation diaries, they write down what food they eat all week. And some of it is based on some limited measurements, but mostly not in the United States. So a big problem there is that the data are coming from lots of kind of unreliable sources. So this is like a long way of saying that we don't have great data on households. We do ask people. We say like, when we do surveys, we'll say like, here's a milk jug, it's a gallon, like how many milk jugs of food waste do you think you might fill up every week? But people are notoriously kind of bad about estimating that. So a lot of times we just either base it on these published literature estimates, we try to ask it directly, recognizing the challenges in that, or we kind of work our solutions to be like generation agnostic. So hopefully that answers the question. It's like a long answer.
Thank you so much. Hold on, Mike, I will unmute you. Hang on a second, please. Please go ahead, and if you can unmute your microphone, it is still on mute.
Thank you. Callie, great presentation. Thank you so much. So great answer to my question, but do you have even any guesses about the magnitude of residential versus commercial institutional? Is it, 25-75, 50-50?
Most of the estimates estimate between 30 to 50% of the total waste in the United States is happening at the household level. Okay. And then there's Oregon actually did a really interesting study that has some better data, and I can try to find that and send it to you. They even went a bit further and said how much of that food waste is still edible and how much of it is real waste, like leftovers that could have been eaten. And I think they found out that 70% of the fraction coming out of households could still have been eaten. Wow. And just sort of a side note, I'm in the process now of writing up a paper. We did a survey on consumer house waste or residential house waste during COVID because we started hearing from people, I was much more conscientious about leftovers. I didn't want to go to the store as much, or I bought things online. So we have seen some evidence that people were trying to really put effort towards minimizing that edible fraction. People reported significantly higher rates of planning meals before going to the store, trying to find recipes that would use up what they already have, even eating food past the expiration date on the label, just to kind of avoid having to go out and shop. So I think that's it. But the point is that that sector, there's a huge opportunity there, especially in dense urban environments where it's very closely located. I didn't show it here, but we did have a student who looked at the economies of doing household collection. And I think he found that for a given neighborhood, you had to have about 20 or 30 houses participating before it made economic sense to go pick up curbside waste. In somewhere where in a more urban environment, obviously you're going to get that critical mass sooner, but then you have other challenges like congestion, lack of area for collection of the material. I answered 5 questions there. Sorry.
Thank you. That's great.
Ellie, I have a quick question. Sorry, Nadia. I think some of our students have been studying, Bronx and other zones in New York City have community, they collect composting in a small scale. What do you see as, the city's policy can encourage this kind of behavior? How can we make it more of an economical, sustainable way for local community to also gaining some strength in doing this? I know that you have mentioned about circular economy. So there are some opportunities that we may be able to explore. Would you like to comment on that? Or?
Oh, well, I'm also fascinated to hear about what your students learn from that, because we're very interested in community scale composting. And that one map that I showed is like a geographic map of these 189 companies that are sort of cataloged that do community scale composting. And the majority of them are in the Northeast, and many of them are in New York and around New York City. And so this is clearly going to be a key part of this, because these small scale systems can really operate in a more efficient way where large scale systems don't. And so I think that's kind of where there's that figuring out how they work together. Some of the business models we've seen are like super small scale that kind of band together into a collective. We also see sometimes what will happen is these small scale systems will start and then end up getting bought by like a waste management or a larger firm. So the best approach is a little unclear, but I think they're going to play a really key role. What's also very interesting is then when you look more to the West Coast, you see fewer of these, and that's because the municipalities are actually playing a bigger role. So in some cases, it's private firms and nonprofits. In the other cases, the municipality. And so you will see in some areas where it's all handled by the same organization that picks up your recycling and your trash. You just get a green bin for your organics. So that I'm not sure if any research has really compared the two, but I think it's a fascinating question.
Wonderful, thank you.
Right.
Nadia,
thank you so much. Yes, I'm here. Yeah. Right, thank you. All right, so another question is from a graduate student from NYIT in the Environmental Technology and Sustainability program. Her name is Runda Pujara. My apology if I'm pronouncing your name wrong. She wants to ask that, if her question is related to the operation and maintenance of the infrastructure. She wants to know how is it maintained and what are the safety guidelines for people working under those conditions? Thank you.
Yes, that's a fascinating question, because one of the operation is kind of one of the big challenges that we hear from a lot of these companies. And that's both at the small scale and the large scale. So when you go in and look at some of these like small scale waste technologies, like this food waste pulper that I mentioned, I mean, you're dealing with, if you put the wrong thing in there, put metal in there, the whole system gets clogged up and someone's having to dig it all out. Another one of these systems collects the material and then it goes to a grease trap, and there's a number of occupational health and safety issues with maintaining and cleaning those. The other issue is at the very large scale, sometimes the operators at these digesters that are running food waste and manure will tell us like they feel married to the job, because it's running all the time, and they'll get a call at like 3 a.m. that something has gone wrong. And they're like the operation guy, like, no, they're the one person that does it. So one of the challenges is that they're often getting in food waste. It's a little bit of like this kind of consumer mixed waste, but a lot of it's also industrial waste. So when we took a group of students there recently, they had these huge bins full of dessert syrups, like the cherry, the strawberry syrup and the chocolate syrup, and they're like mixing that with manure. But like, that's like a huge vat of this one material. And so sometimes, when they get materials from these industrial companies that have hired them to manage the waste, it's not always the right mixture, so to speak, to have a desired outcome. So if the pH fluctuates, if the volatile solids fluctuate, they can run into some operational problems there. And so they have started tracking, and we do have some data that basically shows like, here's what they're feeding into the digester, and then here's like the performance and the biogas coming out. But it's not super well correlated, I guess, is what I would say. But it's a great question because it's a huge problem.
Yeah, hi, I also wanted to ask, what's the capacity limit? Like, is there something like this much should be filled or this much should be left empty? Like, how much capacity can be filled in a container, like for the digester?
Yeah, that's also an interesting question. There used to be, well, I think there's obviously some safety capacity there because you're dealing with methane and you obviously have to have some pressure and some headspace there for that. But the bigger issue for them a lot of times has been the ratio of, say, like manure to food waste. And there used to be this kind of like idealized ratio of, say, like 80% manure, 20% food waste would give the most biogas yield. But here's what's really fascinating, and this gets to the interaction with policy. Most of these digesters are selling the biogas that they produce, and then they have a gen set on site. They're producing electricity. They're selling it like wholesale, like 2 to 3 cents a kilowatt hour. So they're not making hardly any money on the electricity. Now with the new food waste policy, they can, however, charge higher tipping fees. So they're typically making up most of their money right now on charging company tipping fees to bring it in. So they're bringing in as much food waste as they can, even if it means their biogas yields are relatively low. So they're sort of like, they kind of turn the knob depending on what the economic drivers are.
Also, sorry, I'm asking another question. So what my another question is like, can we use the electricity to run and maintain the operation infrastructure?
There is a lot of the electricity is used on site, but they typically are generating more than is actually required. Where we have seen some really good examples are where, say, like you have a dairy farm at the same place. And so they're taking some of the excess heat that's coming off of this system, and they're using that as like heating and hot water, and for heating and heating water in the dairy itself. So when you have some like heat exchanger matching between the systems, that's where you get a little bit more efficiency.
Okay, thank you so much.
Right, thank you so much. So next question is from Changchi Zhao. And he wants to know any information how it deals with the wasted computer parts, electronic parts, and not just the battery.
I'm sorry. I'm not sure I totally I don't think I totally got it.
Me too, actually. I can unmute the individual and ask him or her to ask this question. Changchi, would you like to please ask this question directly to Callie? I think what they want to know is that, how does the electronic parts wastage work, or what's the situation regarding, or if there is any information regarding that.
Yeah, I mean, food waste, I love all kinds of waste, but my two favorites are food waste and electronic waste. And so we do have a lot of work on electronic waste right now. And that's really fascinating because we've tracked like consumer purchases of electronics over the last 30 years. And so what we're seeing with electronic waste is it's starting to go down in the United States because we're no longer buying a lot of heavy products. But it's getting more complex because we're buying products that rely on a lot of scarce and critical raw materials and resources. So there's some interesting trends happen there. And we actually just have a paper on that I'd be happy to share. But one, just to kind of tie it back to the food waste, is I think that there's also some really interesting examples where we're starting to see integration of IoT or Internet of Things and electronic and more smart technologies, say in the kitchen. And there's a big question about, say, food waste there. So for example, if you put a camera in your refrigerator that you can look at through your smartphone when you're at your store, and it tells you you already have eggs, you don't need to buy more, will that actually result in reduced food waste at the household scale? Or is it just excess consumer spending? Another question being is like, it takes an energy to make these new technologies. Is the savings in food waste enough to offset that initial investment? So those are great questions for the future.
All right, thank you, Callie. I think, let's see if we can have one more question. Roberto, you want to ask your question? I saw you have something in the chat about COVID impact on food waste. Do you want to?
Good. I was trying to find out how to unmute this one. Okay, thank you very much. It's a very nice talk. We saw that we have some kind of waste food at the beginning of the pandemic, especially because many people stopped working, especially bringing to a stall some parts of the food supply chain. But I was wondering, what is your impression about the food waste after that, impacted by COVID? Thank you.
I think it's a fascinating question, and certainly, COVID-19 has certainly torn back the curtain on lots of sustainability challenges, social, economic, and environmental across the country, and food has been a key part of that. Certainly the early reports are that there have been a lot of what we might call like sort of supply-demand mismatches, and a lot of the mega food production is sort of like a huge ship, and it's hard to turn it quickly. And so there's been definitely some evidence that there's been, lots of industrial commercial scale losses when those could not be quickly matched up with what consumers need. At a household level, we focus specifically on New York, and we haven't yet plotted out the data according to the different Cuomo's like zones of New York, or the different, areas that have shut down and opened up at different levels. But we have some initial evidence that consumers at least perceive that they're wasting less at the household scale. And most of that is because they are trying to prevent going to the store as much. But that's then creating a ripple effect back to the store where that supply and demand is mismatched. So I think we're sort of seeing like different trends happening at different scales. And the big impact hasn't really yet been quantified fully.
Okay, we have just one last question, and I think we are right on time. This question is from George Heim, and I would request George, if he wants to ask this question directly to Callie. If I don't hear back from him in a few seconds, and I'll read your questions for you. All right. So he wants to ask actually if the 2020 showed any difference in food waste compared to previous years because of the unusual circumstances, which you already have mentioned regarding COVID-19. But if you want to further mention it, please go ahead.
I think we certainly will probably see that. A lot of our data kind of lags a little bit, like especially the data that we get directly from stakeholders. Like Wegmans, for example, can often provide us data about what's happening at their stores and how much material they put into different bins. So that kind of lags. So we usually don't get that till the end of the year or the next year. So it's a little bit backwards looking. We're sort of hypothesizing that we're going to see some differences there. We also saw, again, getting back to the survey work we did, we definitely saw some different modalities of purchasing. You had a big group of people that moved towards like subscription boxes and trying to buy food directly from farmers and going straight to the producer. And that actually seems to correlate a little bit with increased consumption. Like those groups of people are actually consuming more, but we don't yet have a good retrospective on the year as a whole. I know there are some other groups that are working on similar topics. There's a group at Johns Hopkins, I think, that's doing some similar work. There's also was just a paper published yesterday by a group, I think Albany, Michigan, and Cleveland. There are 3 different areas where they looked at consumer access to food banks. So one thing we saw there is a huge increase in demand, especially with like first-time users of food, food security, safety net, so to speak, like food banks and programs like food cupboards, things like that.
Well, I think with regard to time, we are almost at the clock. And thank you so much, Callie, for this wonderful talk. And for those who still have questions, I think Callie will share her email, and this recording will be posted on our urbanfuel.net website. So please tune in. We have a series of additional webinars on food every other week. So we will looking forward to have you joining us back, and we can collaborate, think about solutions to the current challenge in this system. Thank you very much. I don't know if we can do a virtual collab. Let me see if I can do that. Yeah, thank you very much. Yeah,
I very much enjoyed joining you, and I hope to collaborate with some of you all more in the future.
Definitely. Thank you very much.
All right, thanks. Bye-bye.
Thank you.
Bye.
Bye-bye.